All right, so welcome everyone to the One World Combinatorics on Words seminar. Today our speaker is Matthieu Rosenfeld. So he was recently a postdoc in Liège, and I think now he is in Montpellier. Is that right?
Yes.
And he will speak to us today about a new approach to non-repetitive colorings of graphs of bounded degree.
Okay, thank you, Naraz. I should start by thanking the organizer for the opportunity to present in this seminar. So I'm going to present a new approach to non-repetitive colorings of graphs of bounded degree. I think the interesting part of this title is the new approach part. The non-repetitive coloring of graphs is the pretext. It's just an illustration of the technique I want to present. And so, well, I will start with an even simpler illustration of the technique. But first I need a few definitions, but then I'm going to do a proof in the second slides, which might be a bit weird, but that's what I'm going to do. So first, I'm going to call a square a word of the form UU, where U is non-empty. And then the period of the square is going to be denoted by this U between the bars. It's the length of U, sorry. And this is U between the bars. And then I'm going to say that the word is square free if none of its factors is a square. So for instance, ABC is a square. BC ABC is not square free because BC is a square in the middle. And finally, the word ABC is square free. So you can check that every factor is not a square. Okay. And so now that I have this definition, I can give you the first theorem of this talk, which is going to be disappointing for some of you, maybe most of you, but that's it. So the first theorem is the following. You can avoid squares over arbitrarily long words over the alphabet 1, 2, 3, 4. And I'm going to prove this theorem to you. But in fact, I'm going to show something even stronger, and I need to show something stronger because of the way my proof works. If I denote by Cn the set of square free words of length n over the same alphabet, 1, 2, 3, 4, then I'm going to show that Cn plus 1 is at least twice as large as Cn. And so this is much stronger than the statement of my theorem. And I actually need such a statement because my proof is going to be by induction. And I need a strong inductive statement in order to make my proof work. Okay, so let's go for the proof. So as I told you, I'm going to show my result by induction. So I can suppose that for every I which is smaller than n, I have Ci plus 1 is twice as large as 2Ci. That is, if I add a letter at the right of my word, then, well, I know that the number of square free words is at least twice as large. And then if I use that inductively, I know that if I remove I letters, then the number of square free words is divided by at least 2 to the I. And it's going to be useful in a few sentences. Now I'm going to look at the following set. So what I want to do is I'm going to take Cn, so the square free words of length n, and there are 4 possible letters that I can add, right? It's either 1, 2, 3, or 4. And for each of these letters, either the resulting word is in Cn plus 1, that is, I don't have any square, or it's not in Cn plus 1, in which case I'm going to put it in F. And then the rest of the proof is just to bound F. So F is the set of words which are square free if I remove the last letter, but the last letter creates a square. And I'm going to split this set into smaller sets. So for every integer I, I'll let Fi be the set of words from F that end with a square of period I. And since F, I know that every word of F ends with a square, then f is just the union of all the fi. And so the size of f is at most the sum of the size of the fi. And so if I put that in my previous equation, I know that the size of Cn plus 1 is greater or equal than the size of, than 4 times the size of Cn minus the sum of the size of the fi. So the next step is to bound the size of the fi, and it's going to be quite easy. Indeed, now if I take a word from fi, a word w from fi, then I know that the end of this word is a square of period I. So I know that the last I letters are uniquely determined by the previous I letters. And moreover, if I just remove, if I erase the last I letters, the word is square free. So it's a word from Cn plus 1 minus I, which implies that the number of words in fi is at most the number of words in Cn plus 1 minus I. And that's it. That's the only argument in this proof. Now I can just use all the equation I have and put them together. We've seen earlier that, well, since I'm removing I minus 1 letters from the word from Cn, when I do that, then I can bound this quantity by Cn divided by 2 to the I minus 1. Now, if I go back to my sum, I had that Cn plus 1 was greater or equal than 4Cn minus this sum. And I can just replace the fi by the value I had. I can collect the Cn. And then, well, if you know that 4 minus 2 is equal to 2, you finally deduce that Cn plus 1 is greater or equal than 2Cn. So that's it. This concludes this proof. Regarding this proof, the more complicated argument is, the more advanced argument, I should say, is the fact that you need to know that the sum of this geometric series is 2. And that's it. Then you need to know what is a bijection, and that's basically it. So this is a really short proof that over 4 letters, there are at least 2 to the n square free words of length n. Okay. So as I told before, this result is not really satisfying in the sense that we've known for a while that over 3 letters, so just using 0, 1, and 2, you can actually build infinite words that avoid squares. So in my result, I used 1 more letter than in this result. Still, the proof is interesting. The first thing is my proof holds even in the least settings. That is, if you know that at every step there are 4 colors which are loud, but maybe you don't know that it's 1, 2, 3, 4. Maybe the alphabet can change at every position, then the proof still holds. And also the statement is really simple and tells you that there are exponentially many such words, which we don't have in this result from Thué. Anyway, regarding this result from Thué, which is often seen as the starting point of combinatorics on words, or maybe one of the starting points, it has been generalized in many directions. So I've mentioned some of these directions here. 2 of them are going to be interesting in this talk. I'm going to mention fractional powers, and I'm going to apply the same technique to the avoidability of fractional powers in some particular setting. And the other one is non-repetitive coloring of graphs, which was on the title. So I'm going to apply the same idea to non-repetitive colorings of graphs as well. Okay. So let us start with fractional repetitions. So let me recall some basic definitions maybe. So I'm going to say that a word of the form x, 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 y is a power, and then the exponent of the power is going to be the length of the words divided by the length of the repeated part, which might be fractional, right? I forgot to say that y should be a prefix of x. And then the period of this, or maybe the length of the period of this repetition is going to be the length of x. So following this definition, for instance, ABCAB is a 5 over 3 power. ABA is a 3 over 2 power. And ABAB is a 2 power. So it's a square. So we see that it definitely generalizes properly the notion of square. And then I'm going to say that a word is alpha free for some real number alpha. If it contains no beta power with beta greater or equal than alpha. So this notion has been studied quite a lot, in particular in the context of De Gennes conjecture. So De Gennes conjecture asserts that for any k, maybe it should be greater or equal than 5, there exists a k divided by k minus 1 plus 3 word over k letters. So it's, I think many people and most people in this seminar should know this conference. And so this notion of fractional repetition received a lot of attention in part due to this conjecture that is nowadays not a conjecture anymore. I'm not going to talk about this conjecture, but about another conjecture, which is a bit less famous, I guess. But first I need a few more definitions. So if I take a language L, I'm interested in the growth of this language. Maybe sometime we'll say the growth rate of this language, which is defined to be this quantity, where L subscribed n is the number of words of length n. So maybe a more intuitive way to give this definition is that if I have the growth of the language, then the number of words of length n is roughly given by c times the growth rate to the n, where c is some, it's not a constant, but it's a sub-exponential expression in n. So it's in a way negligible in comparison to gl to the n. So basically it gives you the base of the exponential of the number of words. And then alpha of kx is going to denote the growth of the language of x free words over the alphabet 1 to k. And Schur gave the following conjecture regarding this quantity. So maybe don't look at the values, but basically he says that if you let the size of the alphabet grow to infinity, tends to infinity, you can give precise asymptotics regarding the growth rate of the language avoiding n over n minus 1 powers. And in particular, if we look at the values more carefully, there is something interesting. So basically the previous conjecture, if it's true, it tells you that the graph looks something like that. So on the, so I'm looking at the growth rate of the x3 word over k letters. And what's interesting is, well, obviously this quantity is non-decreasing as a function of x. But if you take a really large car large enough, then the function is going to look something like that. That is, well, I'm not looking at the beginning, but for instance, starting at 5/4, you have this increasing bit. Then there is the value for 4/3, and then there is a huge gap of 1 plus some negligible quantity. And then it increases a little bit of 1 over k. And then once again, you have a huge gap. And basically you have this huge gap at all the values which are of the form n divided by n minus 1. And the rest of the increase is really negligible. So most of the increase in this function is due to these huge gaps that are precisely localized. However, regarding the rest of the function, this increasing bit here is probably not continuous either, and it might have a lot of other nice properties that I don't know. But at least what we can tell is that most of the increase is really in these gaps. So that's why this conjecture is probably interesting. By the way, it only tells you something for x smaller than 2, but we have similar results for when x is greater than 2, and we have the same kind of behavior. That is, the function is also non-decreasing, and most of the increases are due to a few jumps that are precisely localized at integers and stuff like that. Okay, so that's it for the motivation. What I want to show you is, let's go back one slide. I just want to study the first of this of the two equations. So what I'm going to show is the following. So I fix k the size of an alphabet and another integer k, n. And for all I will let ci be the set of n divided by n minus 1 free words of length I over the alphabet 1 to k. And now if I choose some gamma greater than 1 and that respects some condition that maybe we don't have to look at the condition yet, what I can tell is that the number of words I'm going to say of nice words, and by nice I mean words that are n divided by n minus 1 free. So the number of nice words of length I plus 1 is greater or equal than the number of words of length I times gamma. And in particular, we can choose gamma wisely, and we can choose gamma basically to be this quantity. So this is, I'm not going to do this part, but if I can show this lemma, which is the goal of the next slides, then I get this corollary, which maybe it's not really a corollary since you need to do a bit of computations to actually get this result. But basically, if you can take gamma to be something like this quantity, and then you deduce that the growth rate of n divided by n minus 1 free words over k letters looks like is at least k plus 1 minus n minus 1 divided by k. Okay, so my goal now is to show this lemma. This second part is not really interesting. You can give it to Mathematica, it's going to do it for you. So I really want to show this lemma instead. And maybe it's already reminiscent of what we did for squares, because we had the same kind of statement in the end. And I'm also going to do an inductive proof, and I'm going to use the fact that I have a value of gamma with some properties. And the proof is really going to look like the proof we did for squares. Okay, so maybe I just, it's just the previous lemma. I just removed all the unnecessary parts. So I have my two conditions on alpha on gamma. So the first one, which is just gamma greater than 1, and the second one, which I'm not going to use right now. And I want to show that for all I, ci plus 1 is greater or equal than gamma times ci. And I'm going to proceed by induction once again. So I suppose that this holds for an integer smaller than I. And so by using, once again, by using the induction hypothesis repeatedly, I get that for every integer p, basically if I remove p letters, I divide the number of possibilities by gamma to the p. Once again, I introduce the set F. So the set F is the set of words from Ci, well, the set of words that I can obtain by adding a letter at the right of a word of Ci, such that the word is not in Ci plus 1. That is, basically, I add a letter to Ci. If it's still n divided by n minus 1 free, then it goes in Ci plus 1. If it's not, then it goes in F. So naturally, I have these equalities, this equality. And once again, I'm going to, I just want to upper bound the size of F. And in order to do that, I'm going to split F in smaller sets. And once again, for every P, I'm going to let Fp be the set of words from F that ends with a forbidden power of period P. Since every word from F contains, ends with a repetition, I know that f is smaller or equal than the sum of the size of the fp. And I can use that in my previous equation, and I get the following equation. So now the name of the game is to bound the size of fp. Okay, and once again, we can use the exact same idea, because basically, if we have a repetition, we know that the last letters of the repetition can be uniquely determined by the beginning of the repetition, basically. So let's be a bit more precise. So if I take W to be a word from FP, then W can be written UXY, where XY is the repetition. So X is of size P, since I took my word from FP, and Y is a prefix of X. And since it's a repetition, it's at least an n divided by n minus 1 power. So I know that xy divided by x is greater or equal than n over n minus 1. The other thing I know is that if I remove the last letter from y, then the word is n over n minus 1 power 3. So if I remove this letter, it's no more a forbidden repetition. So I know that xy minus 1 divided by x has to be greater than n divided by n minus 1. Now, you can manipulate this equation. I'm not going to do it precisely, but if you have 5 minutes in front of you, you can do it. And you get that the size of y is necessarily p divided by n minus 1. Okay. So now if we look at this word again, so this is W. We know that W ends with the Y part, which is of this length. And this is actually a repetition of this, since it's a prefix of X. So this part is uniquely determined by the prefix of the word. Moreover, if I remove the last letters, I know that I have no repetition in the remaining of the word. So we know that every word of FP is uniquely determined by a word of Ci plus 1 minus P divided by n minus 1, just because there is this simple relation. Now remember, by our induction hypothesis, we know that Ci plus 1 minus this quantity is smaller than Ci divided by gamma to the number of letters I have to remove. So it gives us a nice bound on FP. And now we can use this bound to conclude. So once again, the only smart argument is this argument, which is not that smart. And the rest is simply just doing some basic computations. So now I have this equation, and I'm going to use it to conclude. So recall that in the first slide of this proof, we showed that Ci plus 1 is greater or equal than k times Ci minus the sum of the FP. And we just computed the bound of the FP, so I can just use it. And I can collect the Ci, because this bound, well, maybe I should write, each FP is bounded by Ci divided by something. So I can collect the Ci here. And I get that Ci plus 1 is greater or equal than Ci times this quantity. Remember, by assumption, we took gamma to be greater than 1. So I can simply sum that, and I get that Ci plus 1 is greater than Ci times this quantity. Now we can recall the other assumption of our theorem. The other assumption was this one: k minus n minus 1 times gamma divided by gamma minus 1 is greater or equal than gamma. So that is, this quantity is greater or equal than gamma, which gives Ci plus 1 greater or equal than gamma times Ci. And this concludes the proof. So what we showed, if I go back a few slides, we showed this lemma, right? If I have the right assumption on gamma, then I can conclude that I have this exponential growth, and then the rest of the game is simply to try to optimize gamma to conclude something, and I'm not going to do this part. Okay. So what I showed is the first of this equation. We know that the growth rate of the n divided by n minus 1 free words over k letters is at least this quantity. And the exact same proof can also be used to prove the second statement. There is nothing that changes between the two proofs. Okay, so what is left to do is the other direction, which I am not able to do actually. So there is something really surprising here. It's that it's actually easier in this case to prove a lower bound on the number of solutions and to prove an upper bound, which is usually not the case for this kind of avoidability problems. So Schur was able to prove an upper bound for n lower or equal than 9, I think, maybe it's 10. But the remaining cases are open, but while the upper bounds holds in every cases. Anyway, so this is left open. I'm not going to talk about that more. So let me try to emphasize the idea of the proof, maybe to precise it. So suppose, so let Pn be the number of nice colorings of some object. I'm not going to be more precise than that. And well, just for the sake of explanation, an infinite word can be seen as a coloring of the integers. So it fits now in this context. And then suppose that you can find some coefficient AI such that Pn is greater or equal than C times Pn minus 1 minus this sum. If you look at what we've done, it was always we obtain something like that, right? So we have C colors, and when we color a new element, either it's good and we get into pi n, or it's bad and then we get into f, and then we can express f in terms of colorings of smaller objects. So if we can do something like that, which is purely combinatorial, then, so this is the first step. The first step is in fact to obtain the coefficient, and then you try to find the value of the growth. So now that we have this equation, by induction, you can suppose that pi is greater or equal than beta times pi minus 1 for every I. And by doing that, if you can use, you can express each Pn minus 1 in terms of Pn minus 1. And you get the following equation by collecting the Pn minus 1. And basically now, if you can find C and beta such that beta is greater or equal than this quantity, then you have a proof by induction that beta is a nice, that this is true for every n. So basically the right way to do this kind of proof is the other way around than what we did. You first find the combinatorial property that allows you to write such equation, and then you optimize the beta and the C. Depending on what you want, if you want to minimize the number of colors needed, for instance, you might want to take C to be the minimum over beta of beta plus this sum. Maybe you need to add some constraints so that this sum is defined. Otherwise, you cannot say much. Okay. So this is not really a new idea as such. This idea was already used, or maybe similar ideas were already used in combinatorics on words. For instance, the power series method for pattern avoidance that was introduced by Bell and Go, used by Blanchet, Sardi, and Woodhouse, by Rampersad and by Oshem, relies on the same idea, on the same principle maybe. Also using this idea plus some automata theory plus linear algebra, you can get nice bounds on the growth rate of repetition-free languages. And there is a technique that was introduced by Kolpakov and improved later by Schur to obtain nice bound on the number of square free words and stuff like that. I also used the same idea 2 years ago in the context of avoiding squares under some constraints. So it's definitely not a new idea. It's at least 10 years old in the context of combinatorics and words. But now if you can try to apply it to other contexts, in particular, I want to apply it to graph colorings, hypergraph colorings, SAT, other things like that. Well, it hasn't been done. And in fact, it's really easy to apply the same technique to this setting. So what I'm going to do in the rest of this talk is just to give one example of application of this same idea to graph colorings. That is really recent, actually. Okay. So first, I need to provide some other definitions. We start a new part of this presentation, so I need some new definitions. So a coloring of a graph is said to be non-repetitive if the sequence of colors of any path is square-free. So in this part, I'm going to focus only on colorings of the vertices of graphs, but everything I'm going to say could be studied in the context of coloring of the edges, total coloring, that is coloring of the edges and of the vertices, and some other similar question. And then I'm going to denote by P of G the smallest number of colors in any non-repetitive coloring of the vertices of a graph. And this quantity, I'm going to call it the chromatic non-repetitive number. Non-repetitive chromatic number, yeah, maybe. Non-repetitive chromatic number. So we can start to translate some of the results we've seen in this context. So in particular, the result of Thue can be translated as for any path P, pi of P is at most 3. A simple remark would be to note that the chromatic number of a graph is always smaller or equal to the non-repetitive chromatic number. Obviously, if you have two connected vertices with the same color, so if the coloring is not proper, it cannot be non-repetitive, because if you have two vertices with the same color which are adjacent, then you just have to take this path from the first to the second vertices, and you have a square of period 1. The other thing is that obviously the first question is, can you find graphs where the non-repetitive chromatic number is higher than the chromatic number? There is one such example. So for instance, if you look at this graph, so this is the proper coloring of this graph. It's unique up to isomorphism, but this coloring is not non-repetitive, since if I take this path, I have green, purple, green, purple. And if I want it to be a non-repetitive coloring, I need to add one color. For instance, I can add yellow here. And this is a non-repetitive coloring of this graph. So I need one more color in order to obtain a non-repetitive coloring. Okay. The other definition I need is the definition of least coloring. So what we want to do is we are going to assign a list of k colors to every vertex. And then we want that the coloring that we consider, in the coloring that we consider, each vertex is colored by one of the colors from its list. And what we want is to know how large do you need all the list to be such that you can produce a nice coloring, let's say a proper coloring or a non-repetitive coloring. So let me give an example maybe. If I look at this graph, this really simple graph, this is two colorable, right? I need only two colors to obtain a proper coloring of this graph. Now, if you look at the list coloring question, and I give this list of size 2 to each vertex, so that is each vertex need to take one of the two colors of its list, then it's not possible to obtain a proper coloring. This is because if you look at the colors of the four vertices in the middle, they are all the possible Cartesian products of the two lists on the side, right? If I take green, yellow here, then I cannot color this one. If I take green, red, I cannot color this one. If I take blue, yellow, I cannot color this one. And if I take blue, red, I cannot color this one. So you need lists of size at least 3 to ensure that this graph is list colorable. So the chromatic number of this graph is 2, since two colors are enough to color it. But the choice chromatic number of this graph is 3, since we need list of size at least 3. In fact, 3 is enough in order to ensure that this graph is going to be list colorable. Now we can put all that together. So we are going to give a list of colors to every vertex, and we are interested in non-repetitive colorings that respect the list. And then the quantity which we are going to consider is PCH of G, which is the non-repetitive chromatic choice number of the graph. So the first remark is that obviously the non-repetitive number is at most the non-repetitive choice number of the graph. And in fact, it's not so hard to find graphs where the inequality is strict. And then I can finally give the first positive result. So I think this result was mentioned 2 or 3 weeks ago in the same seminar, but I'm going to mention it once again. So in the rest of this talk, delta is always going to be the maximal degree of the graph. And most of the time, I'm just going to write it delta. And so you have to guess which graph I'm talking about in this context, right? In this statement, it's okay. So Alan and his co-author showed in 2002 that for every graph G, the non-repetitive chromatic choice number of the graph is bounded by delta of G squared times multiplied by some constant. And the proof relies on the Lovász local lemma. And I'm going to, in the few slides, I'm going to provide another proof of this statement that uses the method that I've been mentioning already. But first, let me give a few more examples of results. So first, Gritschuk showed that for any path P, the non-repetitive choice number of the path is at most 4. And this proof uses also the local Lovász lemma. So there are many versions of the local Lovász lemma. I don't remember which one it is, but it doesn't matter that much. It's the Lovász local lemma. And so it was done in 2011. And in 2013, Gritschuk provided another proof of this result that relied on entropy compression. And maybe this proof is a bit easier to read. I don't know, well, whatever. It's another proof of the same result. And if you think about it, what we've done on the second slide, we showed exactly the same thing, because if you remember, I showed that, well, what I showed was we can make 2 to the n words over the alphabet 1, 2, 3, 4 that avoid squares. But in fact, I never used the fact that the alphabet was 1, 2, 3, 4. The only thing that I used was that at every position, I have 4 choices. So in fact, the proof I did was a proof of the exact same result. And this proof is much simpler. By the way, I should mention that using the power theories method, we can also obtain a really simple proof, which is going to be basically as simple as the one I provided in 15 slides ago. Just to illustrate my point, there is a recent survey by David Wood on non-repetitive colorings, and he provides the proof by Gritschuk using the entropy compression method. And this is what I've put in red. So this is the proof using entropy compression. And you should know that somewhere we use the fact that we have bounds on the number of Dick words. So it's not a trivial result. It's also complicated. So in fact, the full proof would be even longer. And in green, this is my version of the same result using the simple technique I've presented. So it's much shorter. And also much simpler. And also it tells you that there are exponentially many such words, which you don't have using entropy compression. Regarding this question, I should also mention that the choice number, the non-repetitive choice number of the pass could in fact be 3 and not, and not 4. So this is a really important open question, and well, I don't know anything about that, but this is an interesting open question. Okay, let's go back to graphs of bounded degree. So as I mentioned, there is this result of Allen and his co-authors, and they showed that, I don't know if it's 2 to the 16, maybe this is wrong. Well, I don't know. They showed that the non-repetitive chromatic number is bounded by delta squared times some constant. And then this constant was improved many times, as you can see here. And there are actually something like at least 10 articles hidden in these many other authors. I think the 5 first proof, they all rely on some version of the local Lovász lemma. This proof and at least 2 of the proofs that are in this last item, they all use entropy compression. One of them used the local cut lemma of Bernstein. One of them used the cluster expansion. So for people that are familiar with this kind of techniques, they always work together. Like these kind of techniques, they do the same things. They are used and applied to the same kind of problems. And what I'm trying to say is that the technique that I'm presenting right now, which is not among this set, should in fact be added to this set of techniques that some people know well. And I'm going to provide, as everybody did, I'm going to provide another proof that the non-repetitive choice number of graph is bounded by delta squared plus a big O of delta to the 5/3. So let's do that. So this is what I'm going to show more precisely. So this is a result that it's a really recent result, whatever. And the result I'm presenting is not exactly mine. Mine, I think, was this coefficient was not as good or something like that. And this is the version from the review from the survey from David Wood. So he improved a bit the presentation and also maybe a bit some coefficient. I don't remember which one. Okay, so this is what I want to show. How will we show that? Well, exactly what we did before. So I'm going to fix a list assignment L of a graph G, and then I will let pi of G and L is a set of non-repetitive coloring of G that respects the list L. Okay, and then under some hypothesis that you might want to skip right now, I'm going to show that if every list is of size at least C, then when I color one more vertex, the number of colorings increases by at least beta. And then once again, the value of beta is this delta minus 1 squared divided by R, where R is some well-chosen real, and C is this quantity. So this is the lemma that I'm actually going to show. And well, using this lemma, if you make the right choice of R, then you can deduce this theorem. So once again, this is mostly computation. You can ask Mathematica to do it. And then you get that this theorem is in fact a corollary of the following lemma. So now let me give a proof of this lemma. And it's going to follow the same step as the two previous proofs of this talk. Okay. First, before I go into the proof, I need one useful observation. It's obviously going to be a bit more complicated because when we add a square in the end of the word, we knew what we had to remove from the square, and it's a bit more complicated in graphs. So I need what I'm going to call the useful observation, which is the following. So what I need is to be able to say how many passes go through one given vertex. Since the number of passes that go through one vertex is going to tell us how many ways we have to choose the square, basically. And so what we have is that if we fix the vertex, the number of passes of length 2s that go through this vertex is at most s times delta minus 1 to the 2s minus 2. Okay, so I'm going to give a short argument of this proof. I'm not going to enter too much into details, but basically we want V to be in this pass. So the first thing we can do is to choose the position of V in this pass. So what we can say is how far away is V to the nearest end of the pass. And so it's either the end of the pass or it's at distance 1, 2, 3, up to s minus 1 of the end of the pass. So we have S choices. Then we have to choose the first neighbor of V. And this first neighbor is going to be the first neighbor in the short end of the pass. So there are delta possibilities. Then we have to choose the second neighbor. And there is at most delta minus 1 possibilities. Why? Because this vertex has to be connected to this one. And this one has degree at most delta. And we already know one of the neighbors. So there is only delta minus 1 remaining possibilities. And we keep going like that. There is also delta minus 1 for the next one, delta minus 1, etc. And then we have to find the long end of the pass. And it's the same thing. There is only delta minus 1 choices for the neighbor of V, and then delta minus 1 choices, etc. So basically, when you choose where is V on the pass, you have S minus 1 possibilities. You have S possibilities. Then for the first vertex, you have delta possibilities. And for all the remaining 2S minus 2 vertices, you have delta minus 1 possibilities. So if you multiply everything, you get that there are at most S times delta minus 1 to the 2S minus 2 such passes. And it's going to be useful in 2 slides, I think. Okay, so let's go back to our lemma regarding non-repetitive colorings. So I have this assumption on beta and C, which we are going to ignore for now. And what I want to show is that pi of GL is greater or equal than beta times pi of G minus VL. And we're going to proceed by induction once again. We can proceed by induction on the number of vertices. So we're going to assume that this is true for every smaller graph. And so what we know now is that if we remove k vertices, then the number of colorings is divided by at least beta to the k. Okay. And once again, I need to introduce the set F, which is the set of bad extension. That is, I take a coloring of G minus V, I color the vertex V, and then maybe it's a good coloring, then it goes in this set. Maybe it's a bad coloring, then it goes in this set. And once again, I want to upper bound the size of F. I need to introduce the same set. So Fi is a set of colorings of F that contains a repetition of length 2i. And then, as previously, we get that F is upper bounded by the sum of the lengths of the sum of the size of the Fi. And this time I'm going to go even further, and I'm going to split each of the Fi into smaller sets. So for any pass P that goes through V, and which is of length 2i, I let Fip be the subset of Fi such that there is a repetition along P. So since every repetition of length 2p has to be on a pass of length 2p, I know that Fi is the sum of the Fip over every possible passes going through V. So this is why the previous lemma was useful. We bounded the number of such passes. Okay. So in order to bound Fi, we need to bound Fip. So that's what we are going to do. So fix some P and let P prime be the half of P that contains V. So for instance, if I take my drawing, so this is, I'm considering this pass, the horizontal pass, and then P prime are the two vertices on the left, because this is the half of the square which contains V. Now we know that if there is a coloring that has a square along this pass, then the colors of the two left vertices, or in general the color of P prime, is uniquely determined by the rest of the coloring, because this is a square and this is the rest of the coloring repeated. Thus, and moreover, the rest of the coloring is square free. So we know that the rest of the coloring belongs to pi of G minus P prime. So each coloring of pi of G minus P prime determines a unique coloring of Fip, at most a unique coloring of Fip. So we know that the size of Fip is bounded by the size of by the number of non-repetitive coloring of G minus P prime. Now, if we can use our induction hypothesis, since P prime is of size I, if we remove all the element of, if we color all the element of P prime other than V, then we get the following equation. We have to multiply by beta to the 1 minus I. And this is an interesting bound on Fip. And in order to bound Fi, we need to sum over every passes. So this is the left part here is just the size of Fip. And this is the number of passes. This was the useful observation, told us that the number of passes of length 2 to the s going through a vertex, through a given vertex, is I times delta times delta minus 1 to the 2s minus 2. This should be I, not s, sorry. This is a mistake, and here also it should be I. Now, you probably don't remember, but beta was defined to be delta minus 1 squared divided by r. So I'm just replacing beta by its value. And then I'm just simplifying the delta minus 1 squared to 1 minus I cancels out with this part. And we get this. So we now have a bound on Fi. And we will be able to conclude. So remember that F was bounded by the sum of the Fi. So we can use the bound that we had in the previous slide. We simply have this, this sum, which is easy to simplify. Remember that R was chosen to be between 0 and 1, so we can perfectly go from this to the next expression. And now that F is bounded, we can conclude. remember that we had the number of coloring of G was at most C times number of coloring of G minus V minus F, which we can replace by that. Now we can collect this part, and I'm going to do it the other way around. You don't remember, but C was defined to be beta plus delta divided by 1 minus R squared. So if we replace C on this equation, we can see that the delta divided by 1 minus R squared cancels out. And so it only remains beta times pi of T minus V. So this was a bit more technical, but still without any advanced argument, we were able to show something interesting, let's say, that the number of colorings increases by at least beta with some well-chosen value of beta when you color one more vertex. Okay, so I'm just going to put the theorem back for a second, sorry. So on the bottom we obtain this result. And once again, just now by choosing the right value of beta, you get to this. This is not the interesting part because you can just ask for minimize C by going through all the possible values of beta, and Mathematica can do that really efficiently. Okay, so so this technique was the first. As far as I know, the first use of this technique was in an article that I've put on the archive on June of this year. And since then, there are 3 other articles that use the same technique. In particular, there is an article from Van Les and Wood, where they apply the same technique to hypergraph colorings. I'm not going to define it, but basically, we obtain this result, which is a new result. We could obtain similar results using local Lovász lemma, but this is slightly stronger. And the other thing is, in this result, they know that there are exponentially many satisfying colorings, which was not the case with the LLL local Lovász lemma version of the theorem. And they also applied the same idea to SAT problems. So maybe don't go through the theorems because they are a bit annoying to read or something. And it's been also applied to other techniques. So since then, it has been applied to star coloring, frugal coloring, total non-repetitive colorings, and weak total non-repetitive colorings. I've also applied it to avoidability of fractional powers. That's what we did earlier. So this is not really new because this is in the topic of combinatorics and words, and this technique was already, let's say, similar techniques were already known inside combinatorics and words. And in the recent survey of David Wood, he also applied it to some other non-repetitive questions, with every time it's the same idea repeated. Okay, so I think what I wanted to show is this. Well, I wanted to explain this technique. I hope that this was clear enough to give you an idea of what is this technique, and it's actually really simple to use. And the other thing is, well, this technique was already used in combinatorics and words, but it had never been applied to any other field as far as I know, like graph theory or hypergraph or SAT. And it was actually kind of simple to, maybe not simple, but it was doable to apply the same idea to graph theory and other topics. And it actually provided really good results with simple proofs. So that's something, I guess. The other thing I've been mentioning, entropy compression and Lovász local lemma a bunch of time. And I think this technique is actually equivalent to these 2 techniques in terms of what you can prove for the number of colors, for instance. But the proof that we get are much simpler. And it also tells you every time that you have exponentially many solutions or something like that, which is something that you didn't add you didn't have with entropy compression. Something I would be interested in would be to find other applications to this technique, and I think there should be many other applications. And the technique is so simple in a way that, well, if you want to try it, to apply it to an application, it might take you 10 minutes to try to apply it to a given problem once you've understood the technique. The other thing is that in the context of combinatorics and words, we are able to use it in better ways, let's say. So as I told you, Kolpakov and Schur used it to use the similar idea plus linear algebra plus automaton to compute precise lower bounds on the number of square free words. And for that, you need basically good bounds on the coefficient of the AI of your infinite sum. And this is done by using computers. So I have not been able to do the same thing for graphs, but maybe there is a way to do some local exploration or something to obtain good coefficient for the AI in the case of graph, hypergraphs, and other problems like that. Okay, so that's it. Thank you for your attention.
Thank you very much, Matthieu. Does anyone have maybe a quick question for Matthieu? No questions for Matthieu. All right.